let's start so we're not just sitting here awkwardly staring at each other. So welcome to the Color, Light, and Photography panel. I am a painter, so I am super excited to get to ask these panelists all sorts of questions about how does color work, really. And with that, I will let them introduce themselves.
Good evening. My name is Torrey Stenmark. I am an organic chemist. I am also a costumer. So my primary experience around color is actually through fabric dyes. I teach my students the chemistry of fabric dyes, and I use them myself in a lot of my costuming. Also, as a costumer, I am very familiar with the problem of what color is that thing and what color does it photograph, which are two different problems. Yeah, I am very excited to be here.
I am Paul Currie. I am a biologist, chemist, veterinarian, emergency manager by training. So, you know, pick your field and stick with it. I am a wildlife photographer and cosplay photographer and have been doing that for well over a decade. And I am a person that uses natural light in my photography. And so paying attention to all those fancy settings on the camera is what I do.
Good evening, everybody. I'm Joseph Meany. During the day, I'm a materials scientist and chemist with Savannah River National Laboratory. In a previous life, I was an application scientist for a spectrophotometer manufacturer, which is fancy speak for I got to make science rainbows for all sorts of reasons. During the night, I'm on the board of directors for the Interstellar Research Group, a nonprofit advocacy organization for interstellar travel and flight. And I have a 2018 book on the supermaterial graphene. So if you like books about science, take a look.
So I have a question. What is light?
Okay, so this is literally breaking news, okay? I mean, this is something that came out just the other day, and it was so fresh that I didn't even actually get to digest the full article. But basically what it boils down to is who here has heard of the particle wave duality? Right? Okay, most of us here have heard it. For those of you that don't know about the particle wave duality, there's an argument in science about whether light is a wave or a particle or both. And the recent determination has actually quantified how much of light is a particle and how much of light is a wave. Do any of the other co-panelists, have they read that same?
I saw it on my feed, but I didn't actually get a chance to read it.
Right. So the way that they did it was they were like, okay, let's take some 2 photons and let's do a double slit experiment where they treated the light like a photon, and they took the same type of photon and tried to specifically treat it like a particle, and showed that there was an imbalance, there was an asymmetry between the way that the particle behavior could be measured against the wave behavior. So the particle wave duality is a thing, but it's not actually 50-50, and that is insane.
Wow.
So ultimately, the answer to the question is yes.
Yeah, it's both, but not both at the same time in equal quantities.
So then, what is
Schrödinger's particle?
color?
So color,
Color is literally a pigment of your imagination.
yeah.
I mean, yes, it's a bad pun, but at the same instance, it's also true.
No.
No. I'm going to leave it to the spectrophotometer to do this.
Okay. Okay, so energy, right? We've got microwaves, gamma rays, radio waves. All of them are waves. All of them are energy. All of them technically are light, but not all of them are color. The only light waves that are color actually sit between wavelengths of 400 and 700 nanometers. We've got some fantastic folks here repping the rainbows on their bodies and on their faces. And so everything in between the violet and red portion of the electromagnetic spectrum actually only occurs within a wavelength, a length from peak to peak of the wave aspect of light. But you can also look at the fact that, okay, these light waves, these radio waves, these gamma rays, they exist across 27 orders of magnitude in wavelength. There is an incredible diversity in the amount of energy that can be carried by a single photon. And depending on that energy, you're getting different types of information when this light reacts with a chemical system. So color, specifically what we're talking about, the visible range of the spectrum, is when a photon of an appropriate wavelength hits a receptor in your eye, and your eye picks up that information and gets interpreted by your brain. So it is the interpretation of an electrical signal from a chemical reaction that occurs inside your eye.
But wait, there's more. Because once that signal hits your brain, it gets shunted to a different part of your brain called an association area that says, oh, that wavelength is red or blue or chartreuse. Whatever you want to call it, that's all set up in an association area. And that's where the real pigment happens.
So then, did you want to talk about the chemical aspect of it?
Yeah, so when you're looking at a thing and you see that it's a color, whatever color it is, red or blue or chartreuse or whatever, the reason it is that color, and it depends a little bit, of course, on, are we talking about the color of light, or are we talking about the color of an object that the light is bouncing off of? But when you look at an object that is colored, the light hits it, and the molecules in that object absorb some of the light. Which wavelengths of light they absorb depends on the structure of the molecule. Certain molecules have different combinations of carbon-carbon double and single bonds that absorb a lot of light in particular wavelengths. Some of them have metal ions involved, so a lot of copper and iron and magnesium and things like that, different metals. They absorb some light, they reflect other colors of light. And it is the reflected colors that are going to hit your eye and do all the weird brain stuff. I am not a brain stuff scientist. So they do the things these nice gentlemen were telling us about.
So ultimately, what you see as color is everything that the object is not. Yep. So if you have like a green lens, it's not actually a green lens, it's everything but green. So yeah, it's always fun to mess with people's heads with that one.
It's more like a filter. It's blocking out everything that you're not looking for. So
and as was mentioned, this is all energy. So the more colors you absorb, the more energy you absorb. So the ultimate absorber is black, which is why on days like this, when you go outside wearing black, it gets really hot really quick. The worst absorber is white. Bounces off all the colors, which is why it's much better in heat situations.
Which is why the Jedi all wear shades of beige, because the Jedi dress for Tatooine, which is a desert planet, so they wear light colors. And the Sith are just like, we're so cool, we don't actually care about the temperature, we're just all going to wear black all the time.
Well, Tython, it was camouflage. Not Tython, the Korriban. Thank you,
yeah,
Korriban.
So can I throw a wrench into the carbon-carbon single and double bonds?
Yeah?
Okay.
You said the C word in front of him.
So there's a whole beautiful aspect about color that is only just now within the past couple of years being realized. And this thing is called structural color. If any of you were in the Year in Science panel, I alluded to that earlier, but I was merely teasing that to talk about that a little bit more here. So structural color is where a being, and I'll get into more of that later, where a being has actual physical characteristics, actual shapes that will reflect or block or bend or change the trajectory of these light photons in such a way that the ultimate effect that comes out is a color to our eyes.
Are you talking about like butterflies?
I am exactly talking about butterflies.
I absolutely yield the point. In that case, you are correct. It's not carbon-carbon bonds.
Yeah.
Other cases, it is. I stand by it for that.
Yeah. What's up? Oh, we got a question over here. Second row, yeah.
Would that be kind of similar to how you can use a diffraction gradient to separate wavelengths of light?
Yes.
Okay.
That's exactly right. Okay. So butterfly wings have these shapes to them, and in the shapes of the scales is what determines whether you're seeing the white, the blacks, the blues, etc. And a fun early application of this that has only been realized in the past couple of months is some folks took some butterfly scales and put them down onto a glass slide so that the structures were facing upwards. They were acting like little pillars or columns. And when they realized that they could take these structures as a negative template, they cast down a gel as the positive, hardened the gel, and removed that positive layer. And what they ended up with was an anti-reflective coating, right? and so what they could, talk about doing with this is you could make anti-reflective lenses, you could make anti-reflective optics, you can make solar cells more efficient by utilizing these really broad bandwidth anti-reflective coatings. And so by using actual physical structure from nature to be able to enhance these man-made things of ours, I think is something really cool. And these structures can be engineered and optimized in a lab to push those boundaries even further.
Isn't that how we have color information on fossilized dinosaur feathers? Am I remembering that correctly?
Ooh, maybe, but that is not something I remember.
I'm pretty sure that was determined by licking it.
Oh. Of course. Wrong panel.
No, that's Mika McKinnon. She's the one that licks the rocks.
You missed our Please Don't Lick the Science panel earlier today. There's many things you should not lick, it turns out. It's most science.
Yes. Again, do not lick the science. So how does photography work then? How do we get this light into an image that we can look at?
Funny you should ask.
It's not like it's the panel theme or anything.
I know. So we got to have the photographers in their natural habitat here. And, it's all about the lens size. All right. So first off, as we kind of started talking about, you've got to kind of have your eyes, basic little eye primer here. Reflected light comes off the object. It strikes your eyes. It hits receptors at the back of the eye. Humans are weird, really, really weird. After that, it just stops. Almost every other mammal has a mirror at the back of their eye called the tapetum lucidum that then bounces it back through. So they get 2 shots at the light. We only get 1. Right? So they get a little bit better in lower light conditions.
Well, that's unfair.
Well, there's a trade-off, and the trade-off is we get color vision with massive amounts of detail. So sure, a bear can see in the dark, but the bear would see this entire room of people as one object, one just big fuzzy object, and it would kind of just turn around and nope out.
Now
So-
that mirror layer is why your dog or cat looks really creepy in the middle of the night if the light catches it just right? And you go, because its eyes are glowing at you. They're reflecting the light, but it looks like they're glowing, yeah?
Yeah, now here is the catch, right? How well does a cat see in the dark? Absolutely nothing. There is no light. Without light, you can't see. I know, it's the trick question. I'm a professor. You gotta ask those questions.
How well does a cat see in the almost completely but not quite dark?
Twice as well as us. And actually, even more so because they ditch the color vision for more shades of gray. And so they're able to pick up the contrast between the blacks and the whites much better. Again, the trade-off is they lose the detail.
So cats are elves?
Pretty much.
Is that why they sleep in 4-hour increments?
No, that's just because they get things from the mothership just telling them it's the sleep cycle time. All right, so taking the eye, we then go into a camera, and this is your standard single lens reflex camera. Right? A mirrorless camera, just ditch all the mirror stuff and it just goes straight to the sensor. But the way it works, you have an object, it's sending light that's been reflected off of it, it goes through the lens, and then it gets shunted around, and when you push the button, the mirror goes up, and it strikes the sensor or the film, depending on whether you're using digital or not. That's the basics. So, what that really leads to us is when you take a picture, and the literal translation of the word photograph is light painting, right? You are making a quick stop point based off of the amount of light going into the camera. So obviously I didn't get this eagle to pose, right? This is just catching the light as the eagle was flying past after it grabbed that little rockfish that we in no way pulled out of the water and used to bait that particular eagle to get that shot. No, you'd never do that when you're taking wildlife photography. You know, you always want natural looks, right? But I know it's the nature of the beast. Yeah, sorry, you can't not do bad jokes in science. It's just part of the thing. So the catch with the cameras come into the light, right? How much light? And with a camera, there are basically 3 ways to control the light. First off, you have the sensitivity. Now the digital has made this a lot easier. In the old days, when you were still using film, and people still use film because film is a much better resolution than anything the digitals have gotten up to. I think last I heard, well over 100 megapixels is film, versus I think a top of the line is now up to about 30 or so. So yeah, they're amazing. But the catch is, every type of film has a different sensitivity. And the term for sensitivity is ISO. The lower the number, the less sensitive it is to light, which means you can use it when there's more light around. The higher the number, the more sensitive it is to light, but the more likely you are to catch artifacts. So you start to get distortions, particularly if you do some night photography. You will actually see that here in a second. The second way you control the light is by how much you let the lens stay open, the aperture. This is the equivalent of the pupil in your eye. So the more it's open, the more you can see, or the more light that enters. The less it's open, the less light that enters. The catch: the more light you let in through the aperture, the less depth of field you get, and so you can only focus on certain points, and everything beyond that point starts to get blurry. If you want to get a large like crowd shot in here, I would dial down my aperture, close it off a little bit, so that I could get full depth of field and not have whatever row I was focusing on clear and everybody else blurry. Everybody with me so far? The third way is how long I flip my mirror up. The longer I flip the mirror up, obviously, more light comes in. The catch, particularly when you're doing wildlife photography, is the light source is moving. So the longer I leave it up, the more blur I get. So when I'm shooting something like this eagle, I want to make sure my mirror flip is quick. I want to stop that motion as much as I can. That means I'm going to have to compensate by having potentially a higher ISO so that I'm more sensitive to the light and opening up my aperture more. Everybody with me so far on that? Okay. So this is actually towards the end. So that's basically how a camera works.
So are there any situations or things that are really difficult to photograph so they look like how our eyes see them?
Oh, yeah. Okay, go back to the eagle.
Is the dress blue or gold?
What color is Captain Kirk's uniform? Depends on how you answer the question, right? Do you want me to?
Oh, yes.
I was saying, can I
That's
talk
what I was
costumes
hopefully
for a second?
segueing to.
Okay. So what color is Cap? So we have one vote for green. I hear, yeah, right? So that's the question, right? When you look on your TV screen, and we're talking not the dress uniform, which is the weird wrap one is a much more clearly a shade of green. But the sort of classic uniform looks mostly yellow, for the most part, on your TV screen. But the original artifact is green. And it was a combination of weird lighting and the film stock they used, and it shifted way, way yellower than it looked in person. And so if you're going to recreate it, what do? Do you make the green one that was what he was actually wearing on his body, or do you make the yellow one that everyone thinks of when they think of Command, Gold, and Star Trek? And when I made mine, I made the dress version, I sort of agonized over it, and I did like a bunch of different dye tests to settle on a shade of yellow with a little bit of blue mixed into it that I thought read as Kirk's Command Gold. And it was very exhausting, and it was like, little tiny bit more blue, little bit. I did a bunch of tests, and I didn't break into school because, like, I have keys. I just walked into my lab with a bunch of baggies and powders on a weekend and was like, I'm just here to use the analytical balances. Don't mind me. And I did all my dye tests in the organic lab. Or I did the powder, and then I took the powder home and did the dyeing at home. But I masked everything out on the analytical balance because I wanted to be able to replicate it. And as we all know, if you're not writing it down, it's just screwing around. But if you write it down, then it's science. Thank you, Adam Savage.
So while you're on that topic, how do you get those dyes to stick to the fabric?
It depends on the type of dye and the type of fabric. So just for clarity, I didn't dye any of the stuff I'm wearing now, but I do a lot of fabric dyeing. And depending on the type of fabric you're using, if you're using animal-based fabrics, so silk, wool, feathers, anything like that, those are made out of proteins, and you use what are called acid dyes to stick to that, which stick under acidic conditions, and they form covalent bonds between the molecules of the dye, these colored pigments, and the molecules of the fabric. So they form covalent bonds under acidic conditions. If instead of silk, you're working with plant-based fibers, so cotton, rayon, hemp, bamboo, something like that, you use fiber-reactive dyes, which stick under basic conditions. They form different types of covalent bonds, but they'll stick the same, it's the same kind of thing. It's just different molecules with slightly different processes. Any given white fabric has so many sites that the dye can bond to. So it'll stick to the dye, up to a certain amount, and then it's like, nope, it's full, no more, cannot dye it any more vibrant. So you eventually run out where it's like, okay, the fabric's full, I can leave it in the dye bath for another 3 hours with a bunch more dye and nothing else will happen. Yeah.
So would that be similar to how it sticks to canvas as well?
You mean paint?
Yeah.
No.
Are we all gonna have a sigh moment here?
Paint is a different process because that sits for depends on the type of paint, depends on the medium, but it doesn't bond quite the same way. So if you're using a fabric dye, you don't paint with fabric dye, you don't dye with paint. So if you're using like acrylic fabric paint, that sits on top of the fabric, it doesn't chemically bond in the same way. So that's a whole different thing.
So many dyes, many organic dyes are pH dependent on the color that we see to them. Is it possible to use the same molecule under acidic or basic conditions to get different colors on different fabrics?
Yes, I've done it. You don't typically get like a massive color change. It's usually like, shades of blue or whatever you're using. It's not like, you can get some indicators that are absolutely a very dramatic change, but they're not usually used as fabric dyes.
Okay.
But if you use different fabrics, yeah, you can get sometimes a very different, particularly if you're trying to dye like a black. Black is a really hard fabric or color to dye fabric with. And so a lot of blacks are color mixtures that are like some greens and some blacks and blues and stuff. And so if you try that under different pH conditions or different fabric conditions, you will end up with something that skews more, sometimes dramatically green or a little green or something like that.
And actually, that's a really good point. If there are any educators in the audience, what you can do is take a Crayola black marker and a coffee filter, and you can separate out the colors that make up the black marker by using what's called paper chromatography. And that's a really excellent lesson to start exploring some color theory with.
Yeah.
So speaking of color theory, actually, how do you make a color look like a different color other than just messing with the lighting? Or actually, no. How do you lie with photography?
That's great. That's a good question.
So
Without Photoshop.
Was that shot in daytime? Like bright daytime by any chance?
No, well, you could tell by the horizon that it wasn't that. It was actually coming down towards twilight. The trick here is I limited the light. This is not actually photoshopped. This is as shot. And yeah, it's just restricting the light. So I cranked down my ISO. This is like an ISO 100 shot. I cranked up my shutter speed. And I opened the aperture up full because I really kind of wanted to catch the mountains in the background. This is actually looking out at the continent of Antarctica. And I didn't catch it perfect. A few seconds later, there was the infamous green flash as the light dropped below. But it was considerably brighter than what you're seeing, because obviously looking straight into the giant ball of fire. Don't do that.
Plasma.
Okay, I think I see there's some people in the audience
I
with some
stand corrected.
questions, so we probably can start the Q&A section. We will bring the mic to you.
I actually have a question for Tori. So I'm guessing your hair is not real, your actual hair?
I wish it could do this all the time. I really do. But no, you are correct. I'm wearing a wig.
So when you're talking about bonding with synthetics, what's the process there?
So synthetics, the process for if you're dyeing it at home, the process is you should try and go buy it in the right color. You can dye things at home if they are synthetic. They are plastic, polyester, stuff like that. But the best way to get that color in there is to make it is to color as you're making it. So when you've got the plastic fibers, the precursor monomers, melted down, or not melted necessarily, but the precursors, to mix in the coloring agents at that time, and then they're just permanently stuck in there.
So like that's why people mix in the powders when they're using resin and all that, just to incorporate it then.
Exactly, yeah, that's why you'd mix in the powders when you're using resin, is to incorporate it. If you do want to dye synthetic, if you do have a white polyester, if you have a wedding gown you want to repurpose and you want to dye that, you can get dispersed dye, it's called. You'll see it called I-dye poly, or RIT dye is usually that. And they basically just throw everything at it as hard as they can, and some of it sticks, but it will never give you a really good color. That's why I always recommend using silk to dye. If you want to dress, so I made Padme Amidala's Rainbow Lake gown that looks like a rainbow sherbet ice cream cone. And I've seen people try to make it out of polyester, which has sort of the right flow. But if you use silk, it will cost you more, but you will love yourself while you're dyeing it and while you're wearing it. Speaking of optics, when I was a kid, my dad and I used to frequent a telescope store. We would do some amateur astronomy, and they had a sign up in the back of the telescope store: buy the best and only cry once when you pay for it, because you will be happy with those lenses, with those eyepieces, those mirrors, in my case with that silk. When I'm working with silk, it's just so nice to work with and it's nice to wear. And I'm like, okay, cry once, run the credit card, and then be happy with it. So that's really, synthetics are hard.
When you said you're dyeing and you leave it in the dye bath because it's only so much dye combined to that, is that vary by color? Like so much blue could bind to it, and then there's different spots where the red dye could bind, or is it generally all like color blind, basically?
Yeah, it's all going to be the same thing. It's these open sites where some molecule can bind, and most of the color molecules will bind in the same way, the same chemical process. So, if you have a dye that's a very pale color, then you won't see as much of it. If you have a dye that's a very bright color, fewer dye molecules will make a greater amount of visible color at the end. But it's sort of one size fits all for that.
Could any or all of you speak to the differences between absorptive versus emissive colors, specifically when it comes to colors such as like brown, where we don't see it like in the rainbow anywhere? How does that form?
I mean, we were in planning for this panel going to possibly bring up additive versus subtractive color, and emissive versus absorptive color kind of comes into this. So as was addressed earlier, when you have color for our clothing, when you have color for plants or any of the stuff that we see here around us, that is due to light being reflected off of the surface. It is not inherently due to energy being propagated by the material. But when you have fluorescent material, when you have, does anybody in here use L wire in their cosplays? Okay, that stuff is called electroluminescent wire. And that's an emissive process because you are putting power into a cable that is causing electrons to jump up in energy, and when they come back down, they emit the photons of light. The same exact things happens to fluorescent materials when they're lit under black lights, and the same thing actually also happens under black body emission. Now, black body emission is best represented through magma or through iron smelting, blacksmithing, that sort of stuff. So when you get metal, or realistically any material, very, very hot, it will start to glow a color according to its temperature. And there's also all sorts of fancy schmancy math that models how that black body does go ahead and actually emit. And so that's where we see the differences between cool red hots and hot white hots it becomes more white in color because you're emitting more visible wavelength photons. So then when we're talking about color mixing in the additive versus subtractive realms, when you add more colors in the subtractive format, you are getting more and more close to black because you are trending towards absorbing all of the light. When you are working in additive, emissive light realms, you're adding more and more colors together rather than taking them away. So you're getting closer and closer to white. And so I'm sure somebody in here could get deep into the technicalities of RGB and CMYK theater lighting and that sort of stuff. But that's generally how it works, is when you're emitting something, if you have more emitters, you're getting closer to white. When you have more absorbers, you're getting closer to black.
This kind of goes back to not tasting the science. A lot of pigments tend to be toxic. Are there any colors that tend to have more toxic pigments than others, and is there a reason why?
Yeah, don't eat the ones made with chromium, lead, arsenic.
Cadmium.
Cadmium's beautiful.
Yeah, a lot of paints have heavy metals in them, but there's also a lot of pigments that are perfectly edible, and that's natural pigments, right? When you look at food, you get a lot of really good reds and yellows and blues and stuff, just gorgeous colors. And yeah, it's perfectly edible because you got it out of, blueberries or whatever. And those are the ones that are more based around, those carbon-carbon bond structures to give the color, as opposed to, as we said, all of those metal ions that are not tasty. I don't know if there's one color. I think it's just the class of colors, really. I don't think there's one single color that's worse.
Actually, when you go on to the biological ones, reds. Because red, the reason why red is kind of the universal signal for warning is because most things that are red, if you eat it, will kill you.
Except tomatoes.
What if you have an allergy?
If you have an allergy to most things, that's kind of a problem.
That's cheating, right? Because that's a very specific case. It's not a general case of it, yeah.
Yeah, but there are also mineral pigments that are less toxic than others as well. And so things like iron oxides to get the dull reds mixed in, those are generally okay. Like if you mined it out of a rock that was kind of close to the surface of the earth, like that's all well and good. But if you've got some old Fiesta ware from the 1930s, might want to watch out for those red-orange ones because they've got some uranium on the inside.
Wouldn't that make you emissive then?
That would. Okay.
I had to.
That would make you emissive, but you'd be emitting non-visible wavelengths of color, as the decay of uranium emits alpha particles, which are just basically bare helium atoms, as well as tons and tons of gamma radiation. So it's not great for you to keep around. Now, the alpha radiation, it doesn't really travel anywhere. It's buried in the resin used in the plate. But if you take a Geiger counter to one of those plates, you will absolutely pick up that gamma radiation ticks.
I should also put in a little PSA. Just because a pigment is listed as non-toxic does not mean you should eat it anyway.
Don't eat paint, folks.
The question is, would Fiesta Ware keep his food warm for longer? I'm going to go with no.
Well,
unless it's really, really radioactive.
I would say yes, but not in any meaningful sense. Yeah. And there was an article I was reading about this a while ago. Fiesta Ware stopped making the uranium plate, not because it was dangerous to people, but because the company's supply of uranium was taken by the military to make the atomic bomb.
Of course it was. That tracks.
Getting back to photography, why is it so difficult to photograph certain blues and purples and have them actually come out the way that they look to our eyes?
This one is, let's see if I've got my blue. So, as we kind of talked about, color is a pigment of your imagination, and it really is. And as you start moving towards the violet end of the spectrum, you're starting to move into the area that's even harder for your eyes to detect, okay? The red side, you know, they always talk about, well, we'll use red light in low lighting situations because it does minimal exposures. It's actually very easy for your eyes to pick up. When you flip to the other side, it becomes harder and harder to pick up. Same also tends to apply to some of the photographic plates, even the digital ones. And so it doesn't show up and you kind of have to cheat to get it there. The trick here, this one is I literally ran it through a natural filter, that being the water itself, right, to get this effect. This is another one of showing off that color lies, that photography lies. This was taken, it was pretty much pitch black. I could barely see the model. And this was crank up the ISO, have her hold her breath for a while, and flip for about a half second to get this effect. And because it was open so long, the blues tended to show up because it had more of a chance to get them. And that's really the trick when you're starting to go on those kinds of things, is the sensitivity necessary to hit those as you move into the BIV section of the Roy G BIV. It's, yeah, you just got to mess with the sensitivity and give yourself more time.
So with the digital photography, could you talk a little bit about like the number of lenses and the megapixels and how that relate to capturing different colors?
Sure. So megapixels are really somewhat of a lie. Okay? So last I checked, and it's been a while, so my data may be wrong, the human eye at standard photograph size really can pick up the difference between anything less than 10 megapixels. Okay? And so we're doing your standard 4x6 inch. Okay? Anything higher than that, if you're keeping it 4x6 inch, right, it doesn't really matter. Okay? What megapixels actually represent is the number of places, lack of a better term, the pigment is striking the film. Right? The more megapixels you have, the more of those it strikes, and the easier it is to blow up. So the more megapixels you have, the bigger. That's why nothing beats film, because film you can make gigantic, and you don't see the distortions. Here, and this is part of the reason why I brought up this photo, because I had to crank up my ISO, you can see, particularly the blacks, they don't look as crisp as they should. Can you guys even see my cursor when I do this? Yeah. So you can kind of see how the blacks, and it looks kind of grainy, particularly here around the edges. That's because the ISO, the sensor, is so sensitive, it's picking up any figment of light that it can. And so it's causing it to be, and remember how we talked about with dark vision and cat's eyes and stuff like that, shades of grays are great for low light conditions, but they tend to get blurry. They lose that detail, and that's what you're seeing here as the artifacts that I was talking about when you crank up your ISO, and you can kind of see it all throughout this image. That hit on what you were asking. I know I kind of danced around it a little bit.
So I had a question earlier when you were talking about dyeing. What is the mechanism of bleach and how, like, you bleach your hair? When you spill bleach on something, it removes the color. How is that kind of undying things?
So this is a really interesting process here because bleach doesn't actually remove the dye, it destroys the color part of it. So the molecules are all still there, they're just colorless. It does a redox reaction, oxidation reduction, and it damages the molecules so that they become colorless. They're no longer absorbing that colored wavelength of light. It can also do a lot of damage to like everything else in your hair. If you've ever bleached your hair a lot, it gets super frizzy, which is part of why I wear a wig for this, is because the bleach and re-dye process to actually get it to look like this all the time would be expensive, painful, time-consuming, and my hair would be terrible. So, like $35 once, and I can look like this forever. It's great. So the bleach can damage other things. I have a story that shows that I was not paying attention. So I once, a friend of mine had mispurchased a garment that didn't fit him right. He's like, here, do you want this? And it was a blue Nomex coverall. And I went, sure, that's not quite the right color for Ripley from Alien, but I'll throw something on it. And I looked at it, it's Nomex, synthetic fire-resistant material, very polyester. And I thought to myself, I wonder if I just leave this in a little bit of bleach, if that'll get the color out. It did not remove any of the color, but you know what it did do? It dissolved the thread. So I pulled that flight suit out, and it almost disintegrated in my hands, and I had to re-stitch basically every seam in that garment. And every time I'm like, all right, time to kit up as Ripley, I go through and I stick my finger in all the seams to find out where the new holes are I need to fix. Because, yeah, the color's exactly the same, but almost all of the thread dissolved in the bleach. Because I left it in a bucket of, like, I don't even think I diluted it. I think it was straight up laundry bleach overnight. Because I'm smart. I have a master's degree in science, y'all. You can actually do some really cool things once. If you've got, like, a black t-shirt, and you get a bleach pen, like those spot treatment bleach pens, what you do is you take your t-shirt, and you slide a piece of cardboard or whatever in it, and then you go up to your very nice comics author celebrity, and you say, hey, Kelly Sue DeConnick, it's arts and crafts time. Would you sign my t-shirt? And she bleach signed the back. This wasn't here, unfortunately, but she bleach signed the back of my tank top with bleach pen, nice and big. And I let it sit for about 15 minutes and took it to the convention center bathroom and rinsed it off and took it home, washed it. And it didn't actually damage the fabric because I got it washed off pretty quick. It didn't damage the fabric, but I've got this bleach autograph and it's very punk, and I cut the sleeves off because punk.
That's so dope.
Because Carol Core, y'all. There's no Carol Core people here. That's all right.
And there's, in addition to that, we can also talk about photo bleaching, which is essentially the same thing that's going on with light. So we're continuously talking about the absorptivity of properties. When the molecules absorb the energy, that is energy that those molecules can go on and use for chemical reactions. And so the oxygen in our atmosphere, as well as other molecules, ozone, some other things that drift around just naturally in our atmosphere, when the colors are absorbing this energy, whether it be from the sun or from other lights, it's using that energy to undergo a chemical reaction exactly analogous to the bleach idea, and that's why colors are fading over time if you have them in high light areas.
So the question is, how can you more effectively capture reds, white, and black with a camera, especially to keep the exposure correctly with brighter natural lighting?
Let's see. I have a picture for that, sort of. So, again, for those real colors, number one, particularly when you're trying to shoot blacks, you really kind of want to dial down your ISO. Blacks have so much kind of color in them. While they're not that reflective, they reflect lots of other particles, particularly when you're dealing with digital photography, that just give you artifacts. So you want to kind of dial down your sensitivity as best you can. That means that when you're shooting those, you either want to have an artificial light source, your flash photography, if you're doing it in dark conditions. Now, if you're doing it in lighted conditions, like this particular flamingo here, the trick is, and the flamingo's great because they don't move. They just stand there for hours. So, I didn't really have to worry too much about my shutter speed on this. I did open up that aperture wide open. You can tell because pretty much everything a foot behind that flamingo and a foot in front of it is blurry. Right? But actually shooting reds and blacks, particularly in the daylight, it's the easiest side because they show up really well. At night, you have to cheat. You usually have to use a light source. Which brings up a little bit about flash photography. So the catch with flash photography, it is an art form, and I will freely admit it is not one I'm very good at, because the trick is you don't want the flash and the camera to go off at the same time because the light's not there. Remember, this is all about reflected light. But you want the light to be reflected back just as the shutter opens and before it goes. So if you don't have your timing right on your flash, then everything goes wrong. On top of that, think about how your standard flash bulb goes. So it's going to light up one area more than it does another standard light, which is why you'll see a lot of the guys around here will have diffusers around their flashes to try to even out the light source as it strikes to give a more even lighting appearance. Or they will outright set up those giant lights, right? The catch, everything in photography is a trade-off, right? The catch with doing that is if you are going for a specific look on the costume, and this is more on the cosplayer side or the model side, depending on how the cosplay is set up, a lot of times it'll wash out some of the color, and particularly if you've got a lighted costume, you generally won't see the lights. So it becomes a real balance of that. But
I did a costume once that involved UV reactive paint. So it was a Na'vi from Avatar, the blue cat people Avatar, not the good one. I actually love them both. Okay, but I'm not here to defend the plot of Cameron's Avatar. But I did a base layer of blue body paint, and the creatures have bioluminescent dots. So what I did was lay down little UV reactive paint dots, and then had UV LEDs in my longbow prop, so that I could hold it up, and it would shine a very thin strip of UV light on me to make that flash. And it was a very difficult effect to see, and very difficult to capture. But I did once, was going to a con where the photographer had set up a photo booth with a bunch of flash rigs and stuff. And I say, look, I have this UV flashlight in my lab coat pocket. If you want to try to that, he ended up having to pull the dots out with Photoshop. He went through and Photoshopped, or I don't know what program he used, but had to edit them out later because they were there. The camera just couldn't catch the UV light and still being able to see me, but he did pull them up. And that was really cool after the fact.
I think we have time for about 2 more questions, depending on how they go.
I was wondering if you could speak to the idea of hidden colors or colors that shouldn't exist and how you deal with that. Yeah, magentas and blue, true blue yellow and stuff like that.
I'll be honest, I don't deal with them. I'm just happy to have them around, and they don't mess with me. I don't mess with them. We got a good relationship going.
I mean, realistically, Kyle Hill has a whole YouTube video on it, and none of us here could probably do it as much justice as he did.
Yeah.
So I'm resisting the urge to buy a new Fuji camera right now, which means I've been reading a lot about sensors, and there's some kind of thing with like what they call like a Bayer sensor versus an X-trans sensor, which is how many of the red or blue or green pixels you have in the sensor and how they're arranged. Is that related to what you were talking about earlier with this photo, where the blues or things more towards the violet side of the spectrum are harder to grab, and therefore you have to change the ratio of red, green, and blue pixels that you're picking up off a sensor?
I am not as good at that technology as I'd like to be, so my answer is going to be a little bit more theoretical than accurate. But the short answer is that is the intent. Is a lot of this. So there's really kind of two types of photographers out there. There's the group that I tend to belong to, which is the we shoot the natural light. If my flash pops up, it's because it was an accident, right? I don't care what time of day it is. I'm going to shoot it the way it is, and then I'll either play with it in the camera or use Photoshop to cheat. And then there's the ones that do flash or pre-lit. They're the more of your portrait photographers, and trust me, again, like I said, it is an art form. I have a lot of respect for those guys, but the type of camera that you're describing, they tend to lean a little bit more towards the natural light people. And so, kind of like you, I've been doing a little research on it. I just haven't had as much time as I'd like, in part because I'm real happy with the camera I have, and I don't.
You only cried once.
Yeah, I did. Well, actually, I cried multiple times because I have so, photography tip: put your money on the glass, not on the camera. Okay, a better lens. I have a Nikon D40X, which isn't even made anymore. Okay, I can put my nice lens on it and get fantastic photos off of a camera that runs about 10 megapixels. Okay, I can leave it set up on a thing, switch it out for my fancier body, and I'll get almost exactly the same shot with a camera pushing 25, 26 megapixels. I don't remember my number. So yeah, but twice the resolution. How do I tell the difference? I blow it up, and that's how I can see.
We started the panel talking about visible light that we humans can see, right? But we know there are animals that can see wavelengths that we can't. Now, I'm assuming there are cameras that can capture those wavelengths or represent them somehow to us, but how does a camera that captures those wavelengths differ from a normal camera that we use?
Okay, so all photography, first off, got to plug a YouTube video, okay? Go look at Mythbusters YouTube Live, where they brought out Da Vinci again, and they shot Jamie with it. Okay, because this is pretty much how every single type of primitive photography works. Okay, the difference with cameras for the most part is we're dealing with reflected light rather than emitted light. So, but what they do is they have a canvas behind him. Jamie walks out in armor, and they fire paint at him. Okay, and then he moves out of the way, and conveniently, there is the silhouette. Okay. That is how the vast majority of the other types of cameras. So if you're dealing, for example, a X-ray camera, okay? So X-rays make film turn black. So first rule of that. So when you're looking at somebody's radiographs where you see white, that's the area that did not get through, and that's where that person absorbed a little bit of X-ray radiation. Ultrasound. Okay, different structures absorb the sound, and that doesn't bounce back, so it appears darker. Okay, pretty much anything that is a camera that fires to an object into a plate, that's how it works. Is we measure what got through and compare it to what didn't get through, and that's how we figure things out.
Yeah, and for the digital photography side of those sorts of things, Usually there are filters involved, and at that point it's just measuring an electrical signal. Did a photon arrive? Did it not arrive? And so those photons are counted over the time that the exposure was set for. And so like night vision infrared, basically what's happening is an infrared photon is coming in, hits a signal, that signal is processed and then turned into another light that we can see, basically. But if we're giving plugs out here for cool photography, David Attenborough has a Netflix one that's like The Colors of Nature or something of that nature. And in that documentary, it's a multi-part documentary, they go on and do wildlife photography outside of the visible spectrum, and they even take different light polarities as well. So they go into talking about how some species of sand crabs have special lenses in their eyes that, based on the reflections off of the sand, they can tell when a predator is coming from overhead or not, because their eye stalks don't like move in that way. It's really fascinating stuff, the things that people have been able to tell by using photography outside of the visible spectrum.
So because this is one of my favorite stories of all time. This is short, I promise. Okay, how X-rays got their name. So, guy was dealing with a substance, and he had a reactive plate out. He went to lunch. He came back, and he noticed that something had caused an exposure on that plate. There was no lights. There was no nothing. There's just an exposure on the plate. So he said, something had to hit it. I don't know what it is. The most common letter used for the unknown is X. So, X-rays.
Was that Rontgen?
Huh?
Was that Rontgen, Mike?
Yeah, Rontgen.
Okay.
I also want to point out one other way that we can trick the light. So, obviously, walking around with a functioning Shark rocket launcher is not allowed at most conventions.
What?
Killjoys.
I know. But, so this is another trick of photography. I will say this was Photoshop, but it wasn't Photoshop the way you think of it. So that the fire coming out of the back, and if you look closely, you'll actually start to see it. That is a shot of a Roman candle, right? And I just took the sparks off the Roman candle, turned it sideways, and superimposed it. Reason why I mention this is how a lot of ghost photography occurs. This is essentially a double exposure, right? I just did it in post-production rather than on the same plate. But you take a shot, then you take a shot without changing your, and they did it a lot with film, without moving your film forward. And yeah, you get a ghostly image that shows up, and they would say, yes, this is the proof of the ghosts.
And with that, it is 6:30. So if you want to let people know where they can find you in the future.
Thank you for all of your awesome questions.
Absolutely. So if you'd like to see some of my dye work, I am at Tereshkova Costuming on Instagram and Facebook, and I'd love for y'all to find me there.
You can find me at Cthulhu'sChaos.com, which is where I post all my con and wildlife photography.
I'm around the internet at Crimson Alchemist. Most of my Instagram is taking pictures of pretty cocktails.
Thank you, everyone.
Thank you for joining us, folks. The next big panel will be the Fast and Furious Science Watch Party in this room, and then Science versus Movies at 10.